Morning, Physics 20. I hope you guys are all having a good day today. What we're going to look at in today's lesson is power. It's a very powerful lesson. Yeah, pun intended. So, ladies and gentlemen, enjoy the pun on the screen too in your notes. What? How electricity is measured? What? Yeah, it's a good one. So today, ladies and gentlemen, I think for your let's try this again. For your question on power in your assignment, I think I've only put maybe one in there. If COVID wasn't a thing and we were still at school, we'd be spending more time with this one. So this is one of the objectives that is reduced in stature because of the shutdown. Okay, so don't panic too hard about this lesson. It's the one on law of conservation of energy, which is the more important objective. So our previous video is more important than this one in this case, because conservation of energy will haunt you as long as you're doing physics. All right. So, ladies and gentlemen, let us begin. Scroll down. Alrighty. So, ladies and gentlemen, we've got power. Now, power is the rate at which work is done. Now, keyword rate. Now, remember how we talked about how in kinematics that the rate in which distance changes or the rate in which velocity changes mean over time. So the rate in which distance changes is speed, so v equals d over t. The rate in which speed changes is delta v over delta t, which is acceleration. Okay, so in this case, power is work over time. Okay, because it's the rate or how fast energy is used. So if we're talking about a 100-watt bulb, it's going to be using energy a lot faster than it is a 40-watt bulb. Okay. So, although we tend to use LEDs now anyway. So, all right. So, ladies and gentlemen, so how quickly energy is being used in a certain time period. Okay, so if you're going to be looking at the power rating of a particular motor or a particular electric appliance, it's how fast it's burning through that energy. Okay, so here's your equation. Power is either work over time or delta E is over T. Now remember, ladies and gentlemen, that from your previous lessons, that a change in energy is equal to work. So there's two different ways that you may be exposed to a power question. You may be asked to calculate work as in force times distance cosine theta to get power, or you may be given a scenario where energy is changing, and then you would have to calculate a change in energy, be it potential or kinetic or what have you, to calculate power. All right, so ladies and gentlemen, power is equal to watts or joules per second, which makes sense. Joules divided by second. Okay, either unit is fine. Okay, work is in joules, energy is in joules, time in seconds. Oakley dokley. All right, so ladies and gentlemen, think about the old school incandescent light bulbs. They're going to display how many watts the bulb has. So a 60-watt bulb is going to use 60 joules of energy every single second. Okay, so a 100-watt bulb is going to be brighter, but it's going to use 100 joules of energy every second. Okay, sounds good? Cool. Ladies and gentlemen, power is scalar. No direction is needed. And why is power scalar? Energy is scalar. And this equation's about energy. All right. So, ladies and gentlemen, let us begin with our calculations. All right, a 60 kilogram student, so we have mass of 60 kilograms, runs at a constant velocity up a 4-meter incline. Okay, that is an angle of 40 degrees in 4.5 seconds. All right, so theta is 40 degrees and time is 4.5 seconds. And up an incline, up a 4-meter incline. Okay, so I'm going to draw that one there. So let's draw this. So there's level ground. There's our incline, up a 4-meter incline. So this is 4 meters. And here is the student. Okay. And we have an angle of 40 degrees here. Okay, so let's think about this for a moment, ladies and gentlemen. This is a bit of a tricky one. So we need to think about what information do we have in order to solve this problem. Because our two potential solutions, our power is either work over time, or we can use a change in energy over time. Well, in order to get for work over time, work is equal to force times distance times cosine theta. Well, we have distance. Theta, this isn't going to help us with that. It's the slope of an incline. It's not the slope of force. And we don't have force. We don't have anything that we can do to get the force of the student is applying here. So we cannot use this equation because we don't have force. We don't have anything we can use to get force. So we need to think about this one, delta E. Well, are we having a change in energy? Well, we have a constant velocity. Now that's always a key word. So that means, is the kinetic energy of the student changing? No, it isn't. A constant velocity means he's going to be having a constant kinetic energy. So we can't go with a delta EK, but the student's going up an incline. If he's going up an incline, what kind of energy is he gaining? Potential. Absolutely. So here, EP is equal to 0 joules, and we have a height, and here he would have a value of EP. Well, guess what, ladies and gentlemen? We don't have a value of height, but we can get height, okay? So our height initial here is going to be 0 meters, and our height final, well, we can use trig in order to get that. So let's do some trig to get our height final, because we know we're going to be needing it when we use our EP equals mg delta h. All right, so ladies and gentlemen, well, we've got our hypotenuse, we have theta, and we are trying to find the opposite side here. So in order to get h, I am going to need to sine. Okay, do you guys realize that physics puns are a sign of madness? Yeah, if that's the case, I've been bad for ages. So, ladies and gentlemen, let's find the value for our h final over here. So I'm trying to find, so remember, sine of theta is equal to opposite over hypotenuse. And I'm trying to find the opposite, which is my HF. And I'm going to multiply that by my hypotenuse. Okay, so h sine theta is going to give me my opposite, which is the h final, the height final. So my height final is going to be my 4 meters, which is my hypotenuse, times my sine of 40. So plonk that into your calculator, making sure your calculator's in degrees, no rad times here in physics. Get it? Rad, radians. Yeah. Okay. So ladies and gentlemen, we're going to get the lovely height of 2.571 ... meters. Leave all those numbers in your calculators, ladies and gentlemen. So what I'm going to need to do is I'm going to need to calculate my change in energy first. So let's do that, and then we can plonk that into our power formula after. So my change in energy, this is going to be, I guess my step, well, this I guess would be step 1, and then that would be step 2. So my change in energy, in this case, remember, it's potential energy, is going to equal EP final minus EP initial. Remember that according to your data sheet, EP is mg delta h. So the change in energy is going to equal mg h final minus mg H initial. Now, this is the same idea that we were using in earlier videos. I'm going to factor out the mg. These are two different terms, and because the mass of the student is the same, and g is the same, because we're not leaping from one planet to another, I can factor those out. So I'm going to factor out mg, and then I will have my H final minus H initial. Once again, if you don't want to do the factoring to show your work, that's okay. You don't have to. You are welcome to find EP final, EP initial, and then subtract them afterwards if you wish. So the delta E, my mass is 60 kilograms, and my G is 9.81, and my height final is my value over here that we calculated, my 2.571 ... minus my height initial, which is 0. Okay, so there's that method, or ladies and gentlemen, the EPI, that's 0. So what you could have absolutely done so that we didn't have to do all the factoring is just cancel that out because it's 0 joules we starting on the ground. And then you would get your EP final would be the delta E. And you would wind up with the exact same number, because this minus 0 is going to give us our same EP. So just good practice, though, to get into factoring. Okay, so ladies and gentlemen, we are going to get our delta E here. Our delta E is the lovely value of 1513.397 ... joules. Leave those values in your lovely calculators. And then we're going to go on to step 3. So now we have our delta E, and now we can calculate the power. So power is delta E over time. And then we're going to take our delta E, so 1513.39 ... joules. Divide that by time, because we've got time. Get it? We've got time. Yeah. Okay. So divide that by our 4.5 seconds. And I will have to move over here sideways a bit so I don't write on my face. And we're going to get 336.30 watts. Say what? And that's going to be the power, but now we need sig digs. 3 sig digs, 3 sig digs, 3 sig digs, 2 sig digs. So my answer has to be in 2 sig digs. So I'm going to put this into scientific notation. So 3 point, and the 4, that 6 here is going to round that up. So 3, that's a 4. 3.4 times. Let's try this again. There we go. 3.4 times 10 to the power of 2 watts. There we go. I nearly cost myself some points there. All right. It's a little messy. 3.4 times 10 to the power of 2. So, ladies and gentlemen, that is question 1 for power. So, I've got the power. Yay! You know that old song? I got the power. Yeah. Anyway, old song. Old to me, anyway. So, ladies and gentlemen, there's that question. Let's go on to our next one. Alrighty-o. So, we have a 1.00 times 10 to the power of 3 kilogram car. We have the mass. Okay. Accelerates from rest. Okay, so if it's accelerating from rest, that means our VI is going to be 0 meters per second to a velocity of 15 meters per second. So our VF is going to be 15 meters per second in 4 seconds. Okay, calculate the power output of the car in 4 seconds. So we're trying to calculate power. So here, ladies and gentlemen, let's look at what we've got here. So remember, power is equal to work over time, or it's equal to our change in energy over time. So if we have force and distance, then we could absolutely calculate work is with force times distance cosine theta. We have no force, though. We don't even have distance. Then we probably could calculate it. Yeah, we could calculate it with kinematics, but we don't have force. So we have the mass, but we don't have the acceleration, which we could probably calculate that. But hey, we'd have to go use the kinematics equations to calculate force, or to calculate mass, calculate acceleration. We then have to use kinematics equations to calculate distance. And then we would have to do work equals force times distance, or mass times acceleration, in order to get our force. And then we have to multiply that by the distance and then divide it by time. That's not necessary. Whereas, so you could do it if you were really keen. But just don't make your life more difficult than it already is. Just go with the easiest route to get the information. We can use delta E. Keyword from rest. When we are dealing with rest, it means there is no kinetic energy. So we have 0 joules of kinetic energy. Well, we are then going to be accelerating up to a speed. Well, at that point, we have kinetic energy. We can absolutely and very easily calculate the change in kinetic energy and divide that by time. Because we got time. Yeah, we got time. So we've got, oopsie, that's not what I want to do. Let's calculate our change in energy. Now, we're going to be dealing with kinetic because we are moving. So our delta EK is equal to our EK final minus EK initial. We're going to, instead of factoring with this question like we did last time, I'm just going to cancel this out right away because we have 0 joules. We are at rest. So let's now find our delta EK. And EK final, now remember from your data sheet and from last year, EK is our 1/2 mv squared. And so I'm going to find my change in energy, 1/2 times my 1 times 10 to the power of 3, or you can just write it as 1,000 if you want. And my speed is 15 meters per second, and then square that value. Plunk it into your calculator, ladies and gentlemen. You're going to get a lovely delta E of 112,500 joules. Okay, so that's your first step. Your second step is then going to calculate your power. Oopsie. Doop. There we go. Okay, so I've already calculated my delta E, so 112,500 joules. And then you're going to divide that by time, which is 4 seconds. And you're going to wind up with power, 28125 watts. And ladies and gentlemen, as always, sig digs, please. Power scalar, so no direction. Well, I've got 3 sig digs, 3 sig digs, 3 sig digs, 3 sig digs. So I want 3 sig digs. Well, I got a lot more than 3 here. So I'm going to write over here so I don't write on my face. So I'm going to look at my rounding here. Bump, bump. Well, this guy would be there. Yeah, so that's would not round up at all. So I'm going to write my 2.81. And then my decimal, 1, 2, 3, 4 times 10 to the 4 watts. Okay, so ladies and gentlemen, that's question 2. Alrighty-o. Now, one more. 3. One more question for good measure. Because we're having so much fun. More physics. All right. Got a circle here. Let's erase this guy. There we go. All right, a 200-watt motor. Okay, there we go. We've got 200 watts is being used to lift shingles at a constant velocity up to the top of a roof. Okay, constant velocity. So that means we're not going to have a delta E kinetic. Okay, we have kinetic energy, but not a delta E kinetic. Okay, so we can't use that. To the top of a roof. If a pack of shingles has a mass of 28 kilograms determine the speed that the pack will be raised at. Okay. So we are trying to find speed here. So, ladies and gentlemen, we have definitely some interesting stuff to do here. So let's think for a moment, ladies and gentlemen. So we have power, okay? And we are trying to find speed, constant velocity. So that means, okay, well, speed is equal to distance over time. Okay, so ladies and gentlemen, this is a tough question, okay? So we're trying to find time. Okay, how can I find time? Well, ladies and gentlemen, power is equal to work over time. Okay, so if I'm going to find my time, okay, which is right there. So we're going to keep that in mind for now. And now distance. Well, we need distance. Well, ladies and gentlemen, please remember that work is equal to force times distance times cosine theta. Okay, so here our cos theta is going to equal 1 because the force and the direction are going in the same, exactly the same. So they're both going up. Okay, so that means we can cancel out cosine theta. All right, so ladies and gentlemen, now let's think for a moment here. Constant velocity. Our net force is going to be 0. I know. Okay. Our net force is equal to 0. We're moving at a constant velocity. But guess what? We're being moved, this bunch of shingles is being moved upwards. So therefore, we can make an F-net equation. We have a force applied and we have a force of gravity. So in this case, ladies and gentlemen, Fg, see, let's get my eraser here. So Fg is equal to mg, right? Well, if my F net is equal to 0 and force applied minus force of gravity is going to be my F net equation, well, I'm going to add Fg over. So my Fg is going to equal the force applied. So that means the force applied is going to equal mg. So I have the ability, I've got my force, okay, that's good. All right, I have got a location to start with time. Okay, we're going to have to do some equation substitution here, ladies and gentlemen. Okay, because we don't have enough information to plonk numbers in. Now, equation substitution is super important for Physics 30. So please, ladies and gentlemen, pay close attention here. And this is a skill we're definitely going to be using a lot this year. Or not this year, next year. Okay. So, ladies and gentlemen, okay, we have power times time is equal to work. Sounds good? Okay, I've rearranged this equation, so we're going to start with that. Okay, so now what I can do, ladies and gentlemen, is look at this. Work is equal to force times distance. Well, I don't have the ability here to just calculate work, but I can substitute this here into this equation up here. Okay, because power times time is equal to work, and work is equal to force times distance. These two are going to equal each other. So therefore, I can make my power times time equal force times distance. Okay. All right. Now, well, I don't have the distance that this thing is going, so I can rearrange this. But look, I can do the same thing again. I've got distance here. Okay, so we're going to do that. So ladies and gentlemen, what we're going to do is I am going to rearrange this to get my distance. So I'm going to just divide by force. Okay, so distance is equal to power times time divided by force. Okay, now that's going to be the force applied. Well, remember the force applied is equal to mg. Okay, so keep that in mind there. So we could even write in there mg if you want. If you want to go farther into substitution, you can write power times time times mg like that. Okay, so that's that step there. Now I'm going to scroll down because I'm running out of space here. There we go. Okay, so what I need to do now is I need to substitute again. So V is equal to distance over time. Okay, so notice that my distance here is equal to power times time divided by mg. Okay, well, I've got power, I've got time, I've got m, I've got g. So if you wanted, you could plug all this in here. Oh, excuse me, time. We don't have time, so we can't plug that in just yet. Okay, but we have to put this in here now. Take this, replace that distance, because we don't have time. So distance is equal to this. So I'm going to take out that letter D and put that in here. Okay, so power times time divided by mg, okay, divided by time. Okay, so see how I took this thing? This distance is equal to this thing. I can't calculate this because I don't have time, but I can put this in here to replace that. All right, so ladies and gentlemen, I want you guys to look very closely here. Look at what we have here. I'm going to use a yellow pen, so it's kind of like a highlighter. We have time up here. We've got time up here. We've got time down here. Okay. What can I do with these times? Cancel them. I can cancel this time, because the time is going to be mathematically the same. Okay. So I don't need time to solve this equation because it's going to cancel. Now, ladies and gentlemen, my speed is going to equal power divided by mg. That's all that's left, power divided by mg. Okay, so I'm going to put my numbers into my equation. So the power is 200 watts, and we divide that by our mass of 28 kilograms, and g is 9.81 meters per second squared. Plonk your numbers in, and you're going to get a speed of 0.7281 meters per second. And you are going to then, with sig digs, you're going to wind up with a speed of 0.73 meters per second. Okay, so ladies and gentlemen, that's a super tough question. We're going to be doing very little of this level of substitution this year. However, next year in Physics 30, we do this all the time. So it's generally at least once per unit. We've got stuff like this that we got to do, at least. So it's a very important skill that you guys need to do. But it's not a huge focus this year, but more of a kind of a prereq of what's coming up. And Physics 30, it's awesome. What wouldn't be awesome about it? It's physics. So ladies and gentlemen, so if you found this particular substitution question really overwhelming, don't panic about it just yet. That we're not doing a ton with it right now. I just wanted you guys to see kind of what's up and coming for next year. So, ladies and gentlemen, hope you guys have a good day. Give some of the practice problems a try. We've got a few more for you here to work on. And with power, I think I've put like one question on your assignment. Normally there'd be a bunch more and we'd have a test and whatever with this stuff on it. But sadly, no, we don't have that because, well, we're shut down, which sucks. So, ladies and gentlemen, hope you guys have a good day and don't let anything on fire. No fires, injuries, or explosions. And we will see you next video. Now I can't get this thing to stop. There we go. Got that back. I can click on computer. There we go. All right. Have a good day, ladies and gentlemen. See you later.